Hello student, let us move to unit 5 of our paper, which is analog to digital conversion and pulse modulation system. This unit has two portions. First portion is analog to digital conversion and second portion is pulse modulation system. In first portion, that is analog to digital conversion, we'll study how an analog signal can be converted into digital signal. However, the analog signal cannot be directly converted into a digital signal. Rather, it will be first converted into an intermediate signal which is known as discrete signal. Then that intermediate signal, that is discrete signal, that will be converted into a digital signal. The analog signal, which is continuous in time domain as well as continuous in amplitude domain, is first converted into discrete in time domain and continuous in amplitude domain signal. That continuous in amplitude domain and discrete in time domain signal is then converted into discrete in time domain and discrete in amplitude domain signal, which is the final digital signal. So let us move to the first portion where an analog signal is converted into a discrete signal, and that can be done by a process called as sampling. Later on, we'll study how a discrete signal will be converted into a digital signal by the discussion of the corresponding phenomena which is known as quantization. So as you see over here, the sampling is a process of conversion of continuous time signal into discrete time signal. During this process, we always take discrete signal values at discrete time instants or time interval. Now, conversion of that continuous time signal into group of samples is done with a principle, and that is called a sampling theorem. So according to that sampling theorem, a continuous time signal may be completely represented by its samples and can be recovered back if the sampling is done at a sampling frequency greater than or equal to twice of the maximum signal frequency present in the signal. If at the input multiple number of signals are there and if they are combinedly coming to the sampler, there at the sampler what it will do, it will choose the highest incoming frequency and it will sample the signal by the rate twice of that highest incoming frequency, and that incoming frequency is the maximum frequency present in the signal. Now, as I said, the sampling frequency is greater than equal to twice that of message frequency. That has a limiting condition. Limiting condition is that it can be minimum equal to twice that of maximum frequency. That means sampling frequency Fs becomes equal to 2 Fm. So when the sampling frequency Fs becomes equal to 2 Fm, in that case the sampling frequency or sampling rate is known as Nyquist rate. Okay, so as you see over here, it is written when the sampling frequency or rate of sampling is exactly equal to 2 fm samples per second, then it is called a Nyquist rate. And from the value of Nyquist rate, we could able to determine the interval between two consecutive samples by taking the reciprocal of that Nyquist rate, which is otherwise called as Nyquist interval. So as you see over here, the Nyquist interval Ts is equal to reciprocal of sampling frequency, that is 1 upon Fs, which is particularly 1 upon 2 Fm. Now let us move to different types of sampling. There are three types of sampling. First one is instantaneous sampling, which is otherwise called as pulse sampling. The second one is your natural sampling, and the third one is a flat top sampling. So out of these three sampling, the instantaneous sampling is the sampling where the sampling frequency is kept very high. So in that condition, we will have samples at a very close approximation, but that achievement of those samples at a very close proximity is practically not possible. Okay, so this instantaneous sampling is a theoretical concept, it is not practical possible, so it is not used. So as you see over here, it is written that in this sampling the amplitude of sample signal at any instant is equal to the input signal value at that instant, and during that sampling the sampling frequency is kept very high. Let us move to the second type of sampling, that is natural sampling. In natural sampling, what we will do? We will take the sampling frequency as per the requirement, that is greater than equal to 2 FM. So when we take samples with that sampling frequency in natural way, what would happen? We will get train of pulses or sequence of pulses. But the thing is that the amplitude of those sequence of pulses, they follow the amplitude of the analog signal from which the train of pulses or sequence of pulses have been retrieved. Okay, so in that case, what would happen? The samples that we will achieve, they will have certain demerit that we'll discuss later. So as you see over here in this sampling, in natural sampling, the sample signal consists of a sequence of pulses of varying amplitude whose tops are not flat but follows the input signal values. There is a typing mistake. In place of flat, it is written as flat. So you just bear with that, just read out that as flat. So here the condition of sampling is taken as Fs is greater than equal to 2 Fm. The third type of sampling, which is called as flat top sampling, is similar to that of natural sampling, but the difference is that in this case the sequence of pulses, they will have flat tops. So its top is flat, that means the pulses, they will have a constant amplitude. Here also the sampling is done at a sampling frequency greater than equal to 2 FM. The flat top sampling has advantage upon the natural sampling, that it can become helpful in eliminating noise. So it is widely used in comparison to the other two type of sampling. So as you see over here, in case of ideal sampling, the first figure A, that will show the dotted line, that is the analog signal, which is represented by its samples, which is, those are represented by the vertical red lines. Okay. So these samples, they are situated at a sampling interval, that is Ts. If sampling is done at Nyquist rate, then this Ts must be Nyquist interval. Otherwise, it will be a sampling interval. Okay. The second figure B, that indicates natural sampling. As you see over here, the dotted line, which is analog signal, this black dotted line, that will be converted into sequence of pulses, but the amplitude of this sequence of pulses, those are represented by red lines, they are following the amplitude of analog signal. So here what would happen, if the signal will be transmitted from transmitter towards receiver, as you know, during the transmission of signal through the channel, it may come across various type of environmental effect. So there is a probability that some sort of noise may add with that signal. If the amplitude of the sequence of pulses, they will initially be varied. Okay, then what would happen? We could not able to judge how much amount of noise is get added with that signal, because addition of noise make changes in the amplitude. So that difficulty can be eliminated by using the flat top sampling, where the sample sequence of pulses that we'll get, they will have flat tops, that means they will have constant amplitude level. So we do have the value or the idea about the amplitude of the samples initially before transmission. Thereafter at the receiving end, if any sort of error or any sort of change is occur in the amplitude of those pulses, they can be easily eliminate, eliminated by comparing that to the previous value. Okay. Now one term is there which is related to sampling, and that term is aliasing. And this aliasing phenomena, that must be overcome, that must be eliminated during the communication process. And this aliasing is a condition when we will sample a continuous time signal, that means analog signal, with a sampling frequency less than 2 FM. So if we sample a sampling analog signal with a sampling frequency less than 2 FM, then what would happen? The corresponding samples, the consecutive samples, they will overlap with each other. and due to that overlapping, what would happen? The noise will be generated. Okay, and signal cannot easily be retrieved at the receiving end. Fine. So this phenomena, that means a generation of aliasing, that probability must be nullified, and that can be done by using low pass filter, anti-aliasing low pass filters. Okay. So as you see over here, it is written that if a signal is sampled at a sampling rate below 2 FM, then the sampled spectrum will overlap with each other. This overlapping is called as aliasing. Due to aliasing, it is not possible to recover signal from its sampled value where at the receiving end. To avoid aliasing, a low pass filter is used before sampling, which blocks the frequencies which are above FM. And this is the diagram that shows the samples, consecutive samples, when the sampling is done at a normal sampling rate that is greater than equal to 2 FM. So as you see over here, these consecutive bands are there, means samples are there situated at sampling frequency Fs, 2Fs, minus Fs, minus 2Fs likewise, but they are not overlapping with each other. But if we do sampling at a rate less than 2 FM, then what would happen? Each sample will overlap with its neighboring sample. So here see the sample which is situated at Fs frequency, that will overlap with sample which is situated at 2 Fs frequency. So likewise they are get overlapped and aliasing occurs. So let us move to the phase 2 or part 2 of the unit 5, that is pulse modulation. The pulse modulation is a type of modulation in which we bring change in the pulse type of carrier. So as you know, modulation is a process of change in carrier parameter. Okay. So if carrier is analog, in case as we had studied in analog modulation, we did study how the carrier parameters like amplitude, phase, frequency, they have changed. How they have changed? They have changed according to the message signal or instantaneous value of message signal. Here in case of pulse modulation, the carrier is a train of pulse. So the pulse has three parameters. One is amplitude, other one is width, then third one is the position between two consecutive pulses. Okay, so these three parameters, they will change and they will be made to change to generate different types of pulse modulation output. So as it is written over here, in analog modulation system, some parameters of a sinusoidal carrier is varied according to the instantaneous value of the modulating signal. It was studied in the second unit. Okay, some parameters of sinusoidal carrier. In that case, the carrier was sinusoidal. But in this case, in case of pulse modulation method, the carrier is no longer a continuous signal but consists of a pulse train or sequence of pulse. So some parameter of this pulse train varied according to the instantaneous value of the modulating signal. Some parameters means those amplitude, width and position. So this slide shows how the pulse modulation is categorized. The pulse modulation is categorized as pulse amplitude analog modulation, then the pulse digital modulation. In pulse analog modulation, what we will do, we will change the amplitude, width and position of the signal. Which signal? Sequence of pulses are according to the input analog message. Okay. So this is the three things: pulse amplitude modulation, pulse width modulation, pulse position modulation. Thereafter, in pulse digital modulation, we will take continuous pulses, but the thing is that here the analog message signal is first converted into a staircase signal. Staircase signal means sequence of pulses. Okay. Then that staircase signal will be converted into the modulated signal. So that type of modulation is called as pulse digital modulation. Pulse digital modulation is of three types: pulse code modulation, differential pulse code modulation, then delta modulation and adaptive delta modulation. Let us first move to pulse amplitude modulation. As it is written over here, the amplitude of the pulses of the carrier pulse train is varied in accordance with the modulated signal. That is, amplitude of the pulses depends on the value of empty during the time of pulse. Okay, so here as you see in the waveform, the first diagram is the continuous signal, that is a modulating signal or analog signal. Then the second one is a sequence of pulse, that is a carrier signal. Now as per the instantaneous value of the message signal during positive half, when the value of the message signal is increasing, the amplitude of pulse is increasing, and when it is decreasing from positive peak to negative peak, the value of the amplitude of the pulse that will decrease. So it will follow the change in the modulating signal. So that output signal is known as palm signal, and that can be generated by using a sample and hold circuit. So here in this diagram you will have the sample and hold circuit, where it contains two field effect transistor. One field effect transistor is known as sampling switch, the other field effect transistor is known as discharge switch. These two field effect transistor are connected in parallel with a capacitor, across which we will get our overall output. So when we will give the analog input signal as GXT, then what would happen? Then we'll have to switch on the sampling switch, and the sampling switch can be switched on by providing the necessary pulse at its gate terminal. So when we provide trigger pulse at gate terminal G1, the sampling switch is get switched on, and during that period of time we have to kept the discharge switch in off condition. So as the discharge switch is remain in off condition, and as the sampling switch is remain in on condition, so all the incoming current that will flow to the towards the capacitor C, and when it will flow towards the capacitor C, it will charge the capacitor to the maximum value, which is equal to the instantaneous value of the message during that period of time. Okay, and the capacitor will made to hold that value for a certain period of time, and it will hold that value up to which, up to the extent when the discharge switch is switched on. So as soon as the discharge switch is get switched on, during that period of time we have to make the sampling switch off. Okay, so when the discharge switch is get switched on, the capacitor starts to discharge, and the discharge current flows through the discharge switch towards the ground, and the capacitor voltage will drop down to zero value. So in this way you will have the fast pulse. Secondly, so after some time, again the sampling switch is get switched on by applying the necessary pulse at gate terminal G1. Then the capacitor C will charge up to its peak value. During that period of time, the discharge switch is remain off condition. So capacitor will hold the value for certain period of time. Then after certain period, we'll make the sampling switch off and we'll make the discharge switch on. So when the discharge switch is get on, again the capacitor will start discharge. So the capacitor value that will drop down to 0 volt. So in that way, second pulse will generate. So in this way, we will generate the sequence of pulses having different amplitude. So here the overall explanation of the sample and hold circuit is there. So I am just reading out. The sample and hold circuit consists of two field effect transistors, switches, and a capacitor. The sampling switch is closed for a short duration by a short pulse applied to the gate G1 of the transistor. During this period, the capacitor C is quickly charged up to a voltage equal to the instantaneous sample value of the incoming signal. Now the sampling switch is open and the capacitor holds the charge. The discharge switch is then closed by a pulse applied to gate 2 of the other transistor. Due to this, the capacitor is discharged to zero value. The discharges switch is then open and thus capacitor has no voltage remain. Hence the output of the sample and hold circuit consists of sequence of pulses of flat top samples. Then demodulation of palm. In demodulation of palm, we will have a sample and hold circuit again. Here the pulse amplitude modulated signal will first be given to a sampling switch. When it will given to a sampling switch, it will bypass the input current, that will bypass to the capacitor, okay, and charges the capacitor to a maximum value. Okay, then what would happen? Then the switches get opened. Okay, so when the switches get open, the when it will get open during the on non-availability of palm signal, palm pulse. But during that period of time, what would happen? Capacitor will hold the value. Okay. Again, the sampling switch that will be closed when the second pulse will arise. So unless and until the second pulse will arise, the capacitor that will hold the value of the first pulse. When the second pulse will arise, then the switches get closed. Again, the capacitor changes its charging level. So a staircase signal. So in that case, it will attain a different level, a different value. So if we consider different values for all the incoming pulses, so across the capacitor will have a staircase signal having different value. So when that staircase signal having different value will pass through a low pass filter, it will get smoothened out and a continuous signal will be generated, which is our required message. So here the explanation is written. In this method, the received palm signal is allowed to pass through a holding circuit and a low pass filter. In the holding circuit, the switch AC is closed after the arrival of the pulse and it is open at the end of the pulse. In this way, the capacitor C is charged to the pulse amplitude value and it holds this value during the interval between the two pulses. After this, the holding circuit output is smoothened in low pass filter. Palm has certain advantage. What is that? It is the simple process of modulation and demodulation. Transmitter receiver consists of simple and easy to construct. So transmitter receiver circuit construction is very easy, but it has certain disadvantage. What is that disadvantage? The bandwidth required for the transmission of palm signal is very large in comparison to the maximum frequency present in the modulating signal. Since the amplitude of the palm pulses varies, therefore this also varies the power required by the transmitter with modulating signal. So what are its demerits? Demerits is that it requires higher bandwidth and higher power of transmitting antenna or transmitter. So to avoid that, we do require to adopt your pulse width modulation and pulse position modulation method. Those are the advanced pulse modulation system. Okay, so that will cover in the next class. So you can able to follow this portion by following NPTEL website. So this is the link through which you can go to the NPTEL. You can go directly to the NPTEL website, or you can subscribe the video by youtube.com. So this is your reference. So all these are the things that I had to discuss with you regarding the pulse modulation, your analog to digital conversion and pulse amplitude modulation. Thank you for your patient hearing.